Welcome to 2.1 Part 4, Limits of Piecewise Functions. We have already talked about determining limits graphically, and we will be doing that in this section as well, but I'm going to do it both graphically and algebraically. We are going to come up with what this equation actually looks like, what the piecewise function looks like. So we can see f of x in green here is graphed, and it has three different pieces. There's this linear piece that goes from, and I'll put an arrow since I cut those off, that goes from negative infinity to where x is -1. Then there's this quadratic piece that spans from when x is -1 up until when x is 2. And then there is another linear piece, this is a constant function, right, a horizontal line from 2 to infinity. So let's write out what that function looks like. So we'll have f of x, and it's going to have three different parts. Okay, the first thing we need to do is figure out what is the equation for this line. Well, lines are of the form y equals mx plus b, and so our slope here, if we go from point to point, it looks like we're rising 1 and running 1. So our slope is 1. And then if we were to keep going up 1 over 1, we would hit the y-axis up here at 2. So the equation for that line is going to be 1x plus 2, and that occurs when x is less than or equal to -1. All these x's are less than or equal to -1. All right, let's take a look at this middle piece, this quadratic. This one might be a little more difficult to figure out, but this is just the regular old x squared function. We have 0, 0, 1, 1, 2, 4, -1, 1. So this is the x squared function. And yes, this one also looks like we could do the inclusive from -1 to 2. We could have chosen to put the or equal to on the -1 up here or here. They're the same spot. I just chose to put it here. So we can write from, this goes from -1 up until when x is 2. Since it spans from here to here. Again, I could have made this just less than and this one less than or equal to. It doesn't really matter because again, they're at the same point. So we're not really sure which one it includes, but it's at the same point either way. So if you were to plug -1 into this function or this function, you'd get an output of 1 either way. All right, then our final piece is just y equals 3. It's a horizontal line. So that function is just 3, y equals 3. And that occurs when x is just greater than 2. It's only greater than 2 because we have that open circle there, and it goes to infinity. We'll put the arrow. The reason I wanted to start with the picture is because this is what we're more used to seeing. You could find limits using this picture, but I think it's also helpful to see what the piecewise function also looks like. No, you won't have to come up with this on your own, but that's how you can come up with it, is finding the three different pieces, or however many pieces there are. So now we can dive in and find limits using the graph and using the function. Let's look at as x approaches -1, from the left, the right, and then the overall limit. We'll see if that exists. Graphically, we can see that as we approach -1 from the left, our y values are approaching 1, and therefore this limit is 1. As we're approaching -1 from the right, we're also approaching that same y value of 1. Because both our left and right-sided limits are the same number, our overall limit as x approaches -1 is also 1. Now that was done graphically. What if we did not have this graph here? What if you were only given the piecewise function down here? Well, we could still figure it out. In order to do that, we're going to use direct substitution, which is what we've already done and been successful doing. So we want to see as x approaches -1 from the left of our function. Problem is with the piecewise, what piece do you plug it into? Well, if we're approaching -1 from the left, we see that this is where we approach -1 from the left-hand side. These are the values that are less than -1. They're on the left of -1. So approaching -1 from the left, we would have to plug it into this function. So we'll use direct substitution on the top function. and we'll plug in -1 plus 2, and we'll get the value that we got before, which is 1. All right, now if we want to use the algebraic approach to figure out approaching -1 from the right, approaching -1 from the right would have to be this function here, because these are all the x values that are approaching -1 from the right. These are the x values greater than -1, which means we're approaching it from the right. So we'll use direct substitution in for the x squared function and plug in -1, and again get 1. There's really no more work required for this one algebraically. The same rule applies, right? So as long as our left and right-sided limits are the same number, our overall limit is also that number. So we can do this both graphically and using the piecewise function that goes with the graph. Next, let's take a look at as x approaches 2. I'm not even going to really use the graph, but at first I'm just going to do the algebraic way. All right, so as we approach 2 from the left, we have to think about which one we're looking at. Here and here both deal with 2 as like a breaking point. So 2 from the left would mean values less than 2, approaching 2. These are where the x values are less than 2. So we would plug 2 into this function here to use direct substitution. So we'd get 2 squared, which is 4. If we wanted to double check and make sure that was right on the graph, does it look like as we approach 2 from the left, does it look like our y values are approaching 4? Yes. All right, now we're going to approach 2 from the right algebraically. Approaching 2 from the right, we would use this piece down here because these are the x values greater than 2. They're x values to the right of 2. And so we'd use direct substitution here. No matter what we plug in, our output's 3. Okay, and does that make sense graphically? As we approach 2 from the right, do our y values approach 3? Yes, they do. All right, so what is our overall limit as x approaches 2? It does not exist because the left and the right-sided limits, although they both individually exist, they are not the same number. So our overall limit does not exist. Our next example will use some trigonometry. So we have a piecewise defined function g of theta, and kind of like this is an unofficial math term, but like our breaking point is at pi. So we're defined when theta is less than pi, when theta equals pi, and when theta is greater than pi. So we will test out the limit as theta approaches pi from the left first. All right, let's think about where we're approaching pi from the left. That would mean theta values less than pi, which is here. So approaching pi from the left, to find that limit, we would have to use this piece of the piecewise function and use direct substitution for theta. So we will plug in and we'll do 3 sine of pi. All right, the sine of pi is, drum roll, 0. So we'll have 3 times 0, which is 0. Then we want to see what happens as theta approaches pi from the right. Approaching pi from the right would be here, because approaching from the right our value is greater than pi. And so we are going to use direct substitution and plug in here. So we will do -2 cosine of 2 pi, and the cosine of 2 pi is 1, so we'll have -2 times 1, which is -2. All right, so our left and right-sided limits as theta approaches pi exist, but our overall limit as theta approaches pi does not exist because the left and right-sided limits are not the same value. Now, this is an interesting part of a piecewise. The only time our function equals -3 is when theta is exactly pi. So what we could get from that is if you were to ask what is g of pi, if we were to plug in pi, exactly, no limits, this is exact, right? If you plug in pi here, we need to go directly here because that's when theta is pi, we go to this piece of the function, and that would be -3. That's a little extra tidbit there. These last 5 questions will be a you try, so go ahead and get this written down. All right, go ahead and pause the video and then hit play to see your solutions. Here are the solutions. As we approach 2 from the left, we want to look here and use direct substitution. As we approach 2 from the right, we want to look here and use direct substitution. Our left and right-sided limits as k approaches 2 both exist, but since they're not equal, the overall limit as x approaches 2 of k of x does not exist. These were a little bit more challenging, but if you got them, that's great. K of 2, we do not have a place to look for when k is 2. We only know when it's less than or greater than 2 that we can use these, so there's most likely just some open hole where k is 2. So we would say that that's undefined. And for number 5, the limit as x goes to 1, 1 is not a breaking point here, but we can still use direct substitution. Where would we plug in 1? Well, where does 1 belong? 1 belongs here in this piece because 1 is less than 2. And so we would look here and use direct substitution to plug it in, 3 minus 1. All right, so that concludes today's video of limits of piecewise functions. We will be using piecewise functions quite a bit in calculus. They're just something that you see a lot, and I want to make sure that we understand that what they look like, how to work with them, and how to represent them graphically as well.